All right, guys, so we have a skier at the top of this hill. We're given the angle of the hill is 10.5 degrees, measured off the horizontal. We're told that the skier goes 200 meters down this hill, so the length of this incline is 200 meter, like that. And then the skier reaches the flat part and slides to rest. The coefficient of friction for both parts, for the hill and for the flat part, it's the same. So the coefficient of friction, mu, is 0.075 on the hill, and then the coefficient is 0.075 on the flat part. Does that mean that friction is the same on both parts? No, because what's the equation for friction? Coefficient times normal force. So from the hill to the flat part, the coefficient stays the same, but the normal force changes. So we have two different frictions in this problem. Now, what else? Oh, notice the mass of the guy is not mentioned. If mass is not mentioned, what's going to happen? It's going to cancel out. It's going to drop out of the problem. Okay, could you solve this problem purely with forces? Yeah, you could absolutely do it that way. How would you solve this 2 weeks ago before you ever learned to work in energy? You'd use kinematics, but before you could use the kinematics, you'd have to do what?
Free body diagram.
Do free body. So here he is on the hill. Do free body diagram. Sum the forces. What you would do is you would find his acceleration on the hill, and then you would find his acceleration on the flat part. Those are two different accelerations. Once you knew those accelerations, you could figure this out with kinematics. Okay, but we're not going to do it that way. Although I recommend that you try it that way, because when it comes to the midterm, I could give you this problem and tell you to solve it with forces, right? Or I could give you this same problem and say solve it with work and energy. So you got to be able to do things both ways to be the master of physics. And if you want an A in the class, you have to be the master of physics. Even a B, A or B, you're good. You're solid in physics. All right, so how do we do this with work and energy? So here I'm going to revert this, clean this up. So here, this is the idea. Mechanical energy initial plus or minus work non-conservative is going to equal mechanical final. And remember, there's three types of mechanical energy. Now, what makes this problem a little bit tricky, well, first of all, do we have a non-conservative force present?
Yes.
Yeah, what is it? Friction. Everything else, the only other thing doing work in this problem is gravity, and gravity's conservative. So here's the deal. This work non-conservative, let's just call it what it is. It's going to be what? Work of friction, but it's going to be two-part. The work of friction is going to be two parts. Why two parts? Well, the friction on the hill and the friction on the flat part, same or different? Different. So it's two different frictions. Does that make sense? Okay. All right. And is it going to be plus or minus? It's going to be minus. Friction is never going to add mechanical energy. It's going to be minus. So what this is really going to look like, let's start over again. What this is really going to be is we're going to go mechanical energy initial minus work of friction 1 minus work of friction 2 equals mechanical energy final. Okay? All right, so what's mechanical energy initial? Well, I'm going to write the whole thing out. So kinetic initial plus potential of gravity initial plus spring initial minus work of friction 1 minus work of friction 2. And then this is going to be kinetic final, gravity final, spring final. Does this problem have any springs in it? Nope. So now what we're going to do, most of this is going to go away. And look, once you get good at this chapter, do you have to write everything out like that? This is the way I teach it. So like I want you to remember that all these things are a possibility, but a lot of it's going to cancel to zero. So for example, this problem has no springs. Bye-bye springs. Cross out spring energy. Where should we put the 0 point for this problem? On the flat part. I'd put the 0 point, stick the 0 point down here. So this red line right here, that's going to be our 0 point. That's h equals 0. Okay, so this red line right here, that's the 0 point. All right, so does the guy start with kinetic? At the top of the hill up here? No. See right here it says he starts from rest. That means no kinetic. Does he start with potential of gravity? Yeah, he's above the 0 point, so he has potential of gravity. Okay, no spring energy. Okay, so then he goes down the hill. Now over here is going to be our final. So I'm going to erase this C right here. When the guy gets to right here, so here he is on his skis right there. When he gets to there, what's his velocity? 0. So does he end up with kinetic? No. Now look, if you made right here final, would he have kinetic? Yeah, but I'm going to make, so the problem tells us that he hits the flat part and then slides to rest. So over here is the final, okay? So no kinetic. Does he have potential of gravity? No, why not? He's on the 0 point. So here's what we're left with. We're left with potential of gravity initial minus the work of friction 1, which is that's the hill. 1 is the hill, 2 is the flat part. Potential of gravity initial minus the 2 work of frictions is going to equal 0. That's weird. Or is it? Basically, what's happening here? The mechanical energy that he started with at the top of the hill, how much of it gets eaten up by friction? All of it. Friction is just like, I'm taking it all. Every last bit. So just to rearrange this another way, I think it'll be nicer for the algebra, what we're going to say is this. Potential of gravity initial equals work of friction 1 plus work of friction 2. Okay, does that make sense? All right, so now I'm going to erase because I need room for the algebra now. Okay, so I'm going to rewrite that. So remember that. So here's where we were. Okay. Potential of gravity initial equals work of friction 1 plus work of friction 2. Now we plug in equations. All right, what's potential of gravity? mgh. Okay, that's going to equal, now what's the equation for work? Force times displacement. So this is going to be friction 1, which is on the hill, friction 1 multiplied by displacement 1, delta x1. And by the way, what's delta x1? 200. The length of the incline here is 200. Plus friction 2 times delta x2. And by the way, what's delta x2 going to be? That's going to be this distance right here. Should we just call it that? Times d. Let's just call this d. It's this distance down here. That's what we're looking for. All right, now, h. Do we know h yet? No, we do not know h. How do we get our h? Trig. Because what's this hypotenuse here? 200 meters. The angle is 10.5. So h is going to be equal to, this is going to be equal to sine 10.5 times 200 meters. You had to solve for it. So h comes out to be 36.45. 36.45 meters. That's the vertical height the guy starts from. All right, now frictions. We got to plug in for friction here. What's the equation for friction? mu times normal force. So let's find friction 1. When the guy is on the hill, so here I'm going to draw the hill right here. Here's the dude. When the guy is on the hill, the normal force, so to figure out the normal force, you got to do free body diagram. We got mg down, and then normal force like this. So this goes back to chapter 4. There's no way around it. You have to go back to chapter 4. So the normal force has that component and that component. This angle in here is 10.5. It's the angle of the incline. So normal force must be equal to what? To that. So here's what this looks like. So for friction 1, it's going to be, my black pen back. Come on. Come on. Oh, well, I guess I got to do this in brown. Oh, there we go. Okay, so this is going to be mu. Okay, what's the normal force? The normal force for friction 1 is going to be cosine 10.5 times mg. Okay, what's friction 2 going to be? So friction 2 is when he's down here. When he's down here on the flat part, we got mg straight down, normal force straight up. So what's the normal force when he's on the flat part? So it's going to be mu, so it's mu Fn, but that's just going to be mu mg. So these are the frictions. Friction 1 is this. Friction 2 is this. Okay, so let's plug that in. Okay, so we have mgh equals, okay, friction 1 is mu times cosine 10.5 mg, and then what's the distance going to be? 200 meters. Shoot, I'm out of room. Is that parallel? Is the 200 parallel to the friction? Yeah, look, when the guy's going down the hill, which way is the friction pointing? Back like this. Friction is always parallel to the motion. Is friction parallel to the 200? Yeah, it's got to be when you use the work equation. All right, so that's mgh minus, so this is that. Okay, plus, okay, what's friction 2? Friction 2 is going to be mu mg times d. So that's force, right? In both of these cases here, it's force times distance. Here's the force, there's the displacement. Force times displacement. Now look what cancels here. What drops out of this? Mass drops out, and gravity drops out. So we can cancel the g's out. So what we're left with is, you can solve for d. So d, which is what we're looking for, is going to be equal to h minus mu cosine 10.5 times 200 divided by mu. So plugging in, h was 36.45 minus 0.075 cosine 10.5 200 all over 0.075, and this comes out as 289 meters, which is the answer.